Okay, so in this video I'll be recording solutions for the 2020 VCAA Exam 1. Just a reminder that in 2020, due to COVID, the study design was adjusted quite significantly, so there's a lot less probability in these examinations than there are in the normal examinations, so it doesn't assess the full scope of probability. So these are probably not your best practice exams or trial exams in the lead up to the 2021 and 2022 and 2023 exams. Also, it's been probably over 12 months since I've last recorded one of these, so things are a little bit rusty here, so please bear with me. Let's see how things go. Okay, so we've got the VCAA 2020 Exam 1. It is a tech-free examination, so no calculator, but you will always have access to your standard maths methods formula sheet, which I've got over here. Sorry, I've just got, there we go. Which we've got sitting over here. So you'll always have access to this in both exams, but obviously in exam 1 where you don't have your bound reference, the formula sheet's possibly more useful. And it's really important that you're familiar with the formula sheet. The number of times students make errors with things like product rule and quotient rule by, just doing the multiplications the wrong way around or subtracting the wrong way around, it's here on the formula sheet, and there's no reason to get these things wrong. So it's really important that you're familiar. Equally, there's a lot of differentiation and anti-differentiation rules here, and some probability formulas, though they're not particularly useful. The statistical inference formulas are here as well. These weren't relevant to the 2020 paper. In fact, this isn't the formula sheet that was used with the 2020 paper. There was less probability formulas on it. Okay, so let's go back to the exam and let's get going. So all the standard instructions, things to be mindful of. In particular, we're looking at what you can and can't bring into the exam, what you've got in the exam, making sure that you've written your student number and things on it. Unless otherwise indicated, diagrams are not drawn to scale, so we don't get out our ruler or our protractor to measure things. We actually calculate them based on the information. So there's always some more instructions within the booklet, within the particular sections, and these are probably the more important ones. In all questions where a numerical answer is required, an exact value must be given unless otherwise specified. In questions where more than one mark is available, appropriate working must be shown. Okay, and again, unless otherwise indicated, diagrams are not drawn to scale. Okay, let's get going. Question 1 here, no surprises. This is always what question 1 on an exam 1 looks like. It's some differentiation, usually involving product, quotient, or chain rules. So we have find dy dx here. Y is x squared times sine of x, so it's a product of two functions, and so therefore we'll need the product rule. We might want to go over and check our product rule here on our formula sheet. So here it is here. Okay, so the derivative of u times v is u times the derivative of v plus v times the derivative of u. So if we go back over to our exam, we could let u equal and let v equal. I don't tend to do that. It's just first derivative of the first times the second plus first times derivative of the second. So derivative of the first function, derivative of x squared is 2x. We'll leave the second function as it is. Plus in the product rule, check it on your formula sheet if you're not sure, leave the first function as it is, and find the derivative of the second function. So derivative of sine of x is cos of x. Again, if we're not sure, we jump over to our formula sheet, and we see here that the derivative of sine of ax is a times cos of ax. Alright, so we've got cos of x, and there's not really much we can do with simplifying that. We could probably just leave it as it is. I'm just going to remove my multiplication signs. 2x sine of x, sorry my pen's a bit jagged here today, I'm not sure why, x squared cos of x. Okay, so just the 1 mark there, so 1 mark for a correct answer. Evaluate f dash at 1, where f is a function with a domain, all real numbers, and the function has rule e to the x squared minus x plus 3. So this is a composite function. We've got a quadratic inside an exponential, and so it's going to require the chain rule to differentiate it. So we'll first of all focus on finding the derivative, and then we'll worry about finding the derivative when x equals 1. So f dash of x, we're going to use chain rule. Again, you have got the formula for chain rule over here. I don't tend to use this formula, but dy dx is dy du times du dx. So you could let, u equal the inside function, so x squared minus x plus 3, and then use chain rule. I tend to just do it in one swipe. If you've watched my chain rule videos earlier, you'll know how I tend to do that. So imagine sort of covering up the inside function. We've got e to the power of something. The derivative of e to the power of something is still e to the power of something. So it's still going to be e to the power of x squared minus x plus 3. And then we multiply by the derivative of that something, which is 2x minus 1. Now, common error students would make is to leave their answer like that, which is not correct, because order of operations would mean that that is the exponential times 2x only, and then subtracting 1. So it's really important that we're multiplying by all of that. Okay, now, you might write that slightly differently or tidy it up, but we're going to be substituting into it, so I'm not too worried about what the derivative looks like and how neat it is. So f dash of 1, we're going to put 1 into this, so e to the power of 1 squared minus 1 plus 3 times 2 times 1 minus 1. Okay, so 1 squared is 1, take away 1 is 0, and plus 3, so that's just e to the 3. And then in this bracket, 2 times 1 is 2, take away 1 is 1. Alright, so we've just got e cubed. So we've got 2 marks there. One for the derivative, and then one for evaluating that derivative when x equals 1. Okay, question, my file seems to have corrupted a little bit here. There we go. Question 2, straight into some probability. So a car manufacturer is reviewing the performance of its car model X. It's known that at any given 6-month service, the probability of model X requiring an oil change is 17 on 20. The probability of model X requiring an air filter change is 3 on 20. And the probability of model X requiring both is 1 on 20. State the probability that in any given 6-month service, model X will require an air filter change without an oil change. Okay, so this jumps out at me to think about sort of organising this information using a Carnot map or a probability table. So one of the biggest challenges in probability questions is finding the best way to organise the information. And usually once you've organised the information, the answers then are relatively straightforward. So we've got 2 things happening here. We can have an oil change or what's the second thing? An air filter change. So let's have an air filter change is A. We don't need an air filter change is not A. An oil change is O. We don't need an oil change is not O. Now, the other thing we can think about here is there's 2 different ways you can put the information in your Carnot map. And I say that more thinking ahead to part B in the next question. So we can put probabilities in the table, which would mean that the whole table adds to 1. So if we did that, the probability of model X requiring an oil change is 17 on 20. So the probability of an oil change is 17 on 20, which means the probability of no oil change is 3 on 20. Okay. And the probability of model X requiring an air filter change is 3 on 20. So air filter change is 3 on 20, which means no air filter change is 17 on 20. And the probability of model X requiring both is 1 on 20. And then we can fill in the rest of the table. So what we're actually looking for is state the probability that at any given 6-month service, model X will require an air filter change without an oil change. So air filter without oil, it's actually this box that we're interested in here. And so therefore, the probability of needing an air filter change and not an oil change is going to be 3 on 20 minus 1 on 20, which is going to be 2 on 20 or 1 on 10 or 0.1. So it's just a 1-mark question for that answer. Now what I was going to say, and this is relevant to the next part, is there's 2 ways to fill out the Carnot map. So I'm just going to change pen color here, because what I could have done instead, the fact that all the probabilities are given with that common denominator of 20, we could have made the table total 20, okay? Meaning, that the numbers in the table are not probabilities anymore, they're number of things. Okay, so if there were 20 cars serviced, then one of them would have had both 3, 17, 17, 3, and to work out probabilities, obviously you're doing whatever the value in the box is divided by the total number. So sometimes it's just a slightly neater way to fill out the table, and I say that because that's going to become relevant in part B of this question, because I think it sort of makes for some nicer algebra to leave off all the denominators and to make the total of the table add to the denominator. So we'll see part B is pretty much the same sort of question, except they're generalizing it. So a car manufacturer is developing a new model Y. The production goals are that the probability of model Y requiring an oil change at any given 6-month service will be m on m plus n. The probability of model Y requiring an air air filter change will be n on m plus n, and the probability of model y requiring both will be 1 on m plus n. Now these is pretty much the same numbers that we had up here if we think about if m is 17 and n is 3. We've got exactly the same probabilities happening here. So all the same strategies you've used in A, you should be able to use in B. And this is a really important technique in exams. You want to understand that the questions aren't independent of each other. Probably what you've done in part A is designed to help you learn something to enable you to progress to the slightly harder version of it in B. Okay, it's really important that you see those connections. So I'm going to take the same approach. I'm going to use a Carnot, but like I said with the other one, because I don't want all these big ugly fractions everywhere, sorry, let me change my pen back. But because I don't want all these big ugly fractions everywhere, I'm going to think about instead this time, given that I've got all of those fractions I've been given are on m plus n, I'm going to make the total of the table add to m plus n. So this is the sample space basically. Okay, so that means then that the probability of, oil change and not an oil change, probability of requiring an oil change at an even 6-month service will be m on m plus n. So if we were writing probabilities in that the whole table added to m added to 1, then I would have to put m over m plus n in here. But because I'm going to make the table add to m plus n, I'm just going to put m here. It's just going to make the algebra a bit nicer. The probability of model y requiring an air filter change will be n on m plus n. So I'm going to put n here. So the probability, therefore, of this thing happening would be this over this. And then the probability of both is 1 on m plus n, so that would be a 1. And then just the algebra of filling in the rest of the table is easier. So let's focus on what we're trying to find though. Determine m in terms of n if the probability of model y requiring an air filter change without an oil change. So yes, air filter, no oil change. So it's the same one we found previously. It's this box up here we're interested in again. And it's really easy here to see that this is n minus 1, and we don't have to worry too much about sort of subtracting fractions. So therefore, the probability of an air change and not an oil change is going to be n minus 1 over m plus n. Okay, and we know that that has to be 0.05. Okay, so now we just have an equation to solve. So we're going to multiply by m plus n. So we're going to have n minus 1 over m plus n. Now I prefer to work in fractions. 0.05 is 5 on 100, which is 1 on 20. Just it's working with whole numbers. I'm going to cross multiply here, so 20 times n minus 1. I hate cross multiply as a phrase. What I'm really doing is I'm multiplying both sides by 20 and both sides by m plus n. And now let's focus on this next phrase. So determine m in terms of n. Now this is something that students really struggle with. M in terms of n means I'm finding m, determine m. So my answer needs to be m equals. But if it's in terms of n, this thing on this side will have n in it. So I essentially want to make m the subject in the equation that I've got over here. So forget about that as an initial goal. Your initial goal is to just find a way to connect m and n and then worry about getting it in the right form. So if it said determine n in terms of m, we would have had to make n the subject, but we have m in terms of n. So we're going to make m the subject, and that's actually easier here because there's only one m. So we've got 20n take away 20 equals m plus n, and let's subtract n. So let's have m equals 20n minus 1n, so that's 19n take away 20. And there we have m in terms of n. Okay, question 3. Shown below is part of the graph of a period of the function of the form y equals tan ax plus b. Okay, so we've got 2 points. We've got asymptotes, but they're not labelled with equations, so we can't be sure. We can see that there's a y dilation, so potentially a period change, and a horizontal translation. And we can actually see on the graph that there's a horizontal translation. It's gone to the left a little bit here. And so therefore we've got the graph is continuous from -1 to 1. Okay, that looks continuous in the graph as well, so that's just confirming that. Find the value of A and the value of B where A is bigger than 1, A is bigger than 0. Okay, so the y dilation is bigger than 0, which means we'll be dilated, we'll have squashed it in. So the standard period of a tan graph is pi, which would mean that if A was 1, this distance from here to here would be pi. If A is bigger than 0, actually, okay, I was thinking it was bigger than 1. So if A is bigger than 0, if it's somewhere between 0 and 1, then we would have got wider than pi, but if it's bigger than 1, then it's become narrower. So we actually don't have confirmation of which way the dilation is happening. We do know that B is somewhere between 0 and 1, okay? So we've translated the graph clearly to the left because it's positive, okay? So this is a plus something in here. So the graph has definitely gone to the left by an amount that's smaller than 1, okay? And we're seeing that in the diagram as well, in that this, sorry, let me just get a pen. This point here is -1, and so we've clearly gone to the left by something that is smaller than 1. Okay, so, but also what we want to think about is we're really still just looking at like one period of the tan graph, but it's one period of the tan graph. So if we think about our unit circle, we can see one period of tan by going from 0 to pi, but that would be this bit here. Okay, so we're actually not looking at that one period. We're actually looking at a period from, you know, negative pi on 2 to pi on 2, for example, and that's where we're seeing this bit here and this bit back here. So we will sort of want to think about that in terms of domain when we're looking at these things. That's actually becomes quite important in this problem. You can get a bit lost with the wrong solutions or worrying about which solution, but we're really thinking about what's happening with tan only in this range here. Okay, yes, there's then been some dilation and some translation, so it's not negative pi on 2 to pi on 2, but it's still, we're looking at the picture of what happens with tan from there to there. That's how we get this particular shape. Okay, so let's go to the questions. We want to find the values of A and B, and we've got 2 points and 2 unknowns. So we really just want to substitute in our 2 points and create 2 simultaneous equations. So our first point is, well, it doesn't matter which one's the first point. I'm going to go with 1√3, and that's going to give me the equation √3 equals tan of 1A, so A plus B. And then the other point is -1, -1. And that's going to give me the equation -1 equals tan of -A plus B. Okay, so we want to think about some exact values here. So tan equals √3, so I'm going to refer to my special triangles. Half an equilateral triangle with side length of 2. And so if it's equilateral, this is 60 degrees here, which is pi on 3, and this is 30 degrees up here, which is pi on 6. I want tan to be √3, which means this must be the opposite, and this must be the adjacent, opposite and adjacent, and so therefore we must be looking at pi on 3 as our exact value. Tan's positive, okay, so think about where tan's positive, these 2 quadrants here, but as we just discussed, we're really only interested in this region here, so we just want the pi on 3. Okay, so therefore A plus B is going to be equal to pi on 3. Okay, and there's equation 1. Now if we think about our other equation, tan is equal to -1. Okay, so tan equals 1 when our angle is pi on 4. I don't usually need to draw this triangle. Oh, sorry, not √3, √2. So tan of pi on 4 is 1, but tan is -1. Okay, so we must be in these 2 quadrants. But remember, as I said, we're interested in this picture of the tan shape. We can see that from the graph. And so we actually want this one down here. We want negative pi on 4. So that means -A plus B, the thing inside the tan, is going to be equal to negative pi on 4. Okay, so there's our second equation. And so we've got 2 equations with 2 unknowns. We just want to solve simultaneously. If we add these 2 equations together, we're going to eliminate A. A plus -A is 0. B plus B is 2B. And then we'll have pi on 3 plus negative pi on 4. So we're going to need a common denominator there, which is 12. So this is 4 pi on 12 plus minus, that's minus 3 pi on 12. And so 2b is pi on 12, which means b is pi on 12 divided by 2, and that is pi on 24. Alright, so then we need to find a. So we're going to substitute b into whichever equation you prefer. I'm going to go with equation 1. So we're going to have a plus pi on 24 equals pi on 3. Now pi on 3, if we get a common denominator there, is 8 pi on 24. And so therefore a is 8 pi on 24 minus 1 pi on 24, which is 7 pi on 24. And so therefore we have a equals 7 pi on 24 and b equals pi on 24. Don't make it hard for people to find your solution. Let's just talk about the marks here. So how many have we got? We've got 3 marks in this question. Couple of different ways. It could be 1 for both equations and then 1 for each answer. I think the slightly more generous way to do it would be to do 1 for each equation and then 1 for both answers. Otherwise you get pretty stumped if you can't get one of the equations. You've got no opportunity to get either of the other answers. Did we talk about marks in the previous question? The first one was only a 1 mark, so that's nice and easy. The second one here is 2 marks, probably a mark for setting up a valid equation, and then a mark for getting m in terms of n. Okay, question 4, solve the equation. Okay, so fairly straightforward, log equation. So we want to try to combine the logs together. So the first thing that's an issue with that is the 2 out the front here, so that needs to go up into the power. So this is the same as log 2 of x plus 5 squared. Take away log 2 of x plus 9 equals 1. Now we want to combine those logs together, so when we're subtracting logs, we can divide the things inside the logs. So it's log 2 of x plus 5 squared divided by x plus 9 equals 1. Okay, now we want to convert it from a log equation to an exponential. So if log base 2 of that expression equals 1, that means that 2 to the power of 1 is equal to that expression in the log. So that's just simple log facts. And now we have an equation with no logs in it that we can focus on solving. So I'm going to multiply by x plus 9 to get rid of the fraction. So I'm going to have 2 times x plus 9 equals x plus 5 all squared. Let's do some expanding and collecting like terms. So 2x plus 18 equals x squared plus 10x plus 25, remembering how to expand perfect squares properly. It's not x squared plus 25. Collecting like terms, so we'll leave everything on the right. So x squared is positive, we'll take away 2x, so that's going to be 8x, and we'll take away 18, which is 7. Okay, and that factorizes. Factors of 7 that add up to 8 is going to be plus 7 and plus 1. And so then we get either x plus 7 equals 0, which means x equals negative 7, or we get x plus 1 equals 0, and so x equals negative 1. Now, when we have a log equation, we need to make sure that we think about the original domain of the function to make sure that both of our solutions actually fit the original equation. So remembering that whatever's in the log has to be bigger than 0. So this log means that x plus 5 has to be bigger than 0, so x has to be bigger than negative 5. And this log here means that x plus 9 has to be bigger than 0, so x has to be bigger than negative 9. Now both of those things have to be true, and so therefore the domain of this function is x bigger than negative 5. Okay? And so therefore x equals negative 7 is not a solution to this equation. But x has to be bigger than negative 5, so x must be negative 1. When you reject a solution, you need to do so with some kind of statement about why you're doing it. So you should never just ignore. So if you're solving an equation and when you take a square root, there's a plus minus, if you're going to ignore one of them, you should make some statement about why you're ignoring it. So if you're just, if you have x squared equals 3 and you say, I'm just going to write here so you can see what I mean, and you just say x equals root 3, you're making an assumption there that x had to be bigger than 0. And that might be valid for your problem, for the particular question, but you should acknowledge why you ignored the fact that x equals negative root 3 is actually a solution to that equation. Okay, so same thing here. We've got 2 solutions. Algebraically, we can find 2 solutions, but when we consider the problem further, there's a reason why one of them isn't valid, and the reason is this, because the domain is x bigger than negative 5. Okay, so don't just reject without a reason. What have we got here? 3-mark question again. I think probably 1 for getting to the quadratic, definitely, and 1 for obviously only having the one answer. Probably 1 for getting to a point where you've got rid of the logs. might not look exactly the same as that, but a version of that, something like that. Okay, question 5. For a certain population, the probability of a person being born with the specific gene SPGE1 is 3/5. The probability of a person having this gene is independent of any other person in the population having this gene. Okay, so that's telling us it's binomial. In a randomly selected group of 4 people, what is the probability that 3 or more people will have the SPGE gene? Okay, so we're tech-free here, so we're going to need to do a bit of work. So let's set up our binomial. Acknowledge we've understood we have binomial. So x is going to be number of something whenever it's a discrete variable, whenever it's a binomial distribution. So in this case, it's the number of people with the gene, with the SPGE1 gene. And we know x is a binomially distributed variable. We are selecting 4 people, so n is 4, and the probability of any given person having this gene is 3/5. Okay, now that setup's a little less important in a tech-free because the working that you'll have to do in a tech-free indicates that you've understood binomial, but I would strongly encourage that you're always in the habit of setting up your variable and setting up how it's distributed. Okay, so now we want to work out the probability that 3 or more people have the gene. So the probability that x, the number of people with the gene, is bigger than or equal to 3. So that is the probability that x equals 3, or, so plus the probability that x is equal to 4. So we're going to need our binomial formula here. Now I'm pretty sure it's not on our formula sheet. Let's just check though. Probability. No. And so that's a fairly glaring omission that you do need to know your how to calculate the binomial probabilities using the formula. So it is n choose x. So in this case that is 4 choose 3. The probability of success, which is 3/5 to the power of 3. And the probability of failure, which is 2/5, or 1 minus p, to the power of n minus 3. So that's going to be 1 in this case. Plus 4 choose 4, 3/5 to the power of 4, 2/5 to the power of 0. Okay, so 4 choose 3 is 4. Okay, anything choose 1 less than itself is itself, and that's because if you understand that they come from Pascal's triangle, oops, 5, 10, 10, 5, 1. So Pascal's triangle, you just add up the two numbers, sorry, the other way, I did those lines the wrong way. You add up the two numbers above to get each number in the next row. But these are all combinations. So when we're doing NC 1 minus itself, we're looking at the numbers that are on this diagonal here. Okay, so this here is 1 choose 0, this here is 2 choose 1, this here is 3 choose 2, this here is 4 choose 3. Okay, so they're always 1 less than themselves, and it's because it's exactly the same question as if you had chosen to select one thing. Because when you are choosing everything except one thing, it's the same question as if you had chosen one thing. So for example, if we're doing 4 choose 3, we're finding how many ways can I select 3 things if I have 4 things, okay? But that's the same question as how many ways can I choose to not select one thing. And so that's why it's the same as 4 choose 3 is the same as 4 choose 1. Okay, same thing, 20 choose 19 is the same as 20 choose 1, and they'll both just be 20. Okay, so 4 choose 3 is 4. 3/5 to the power of 3. Okay, so 3 cubed is 27, so we're going to need a bit of number work here. 5 cubed is 125 times 2/5 plus 4 choose 4. Anything choose itself is 1. 3/5 to the power of 4, so 3 to the power of 4 is 81. 5 to the power of 4 is 625. And then anything to the power of 0 is 1. Okay, so we've got 4 times 27 times 2. Now you could do that in a couple of different ways. You could do 4 times 27 and then times it by 2. You could do 4 times 2 and then times it by 27. So thinking strategically about what's best. I'm going to do it in the order that it's in actually, because 4 times 27 is not too awful. 4 times 20 is 80 and 4 times 7 is 28. So 80 and 28 is 108. And then we're going to multiply that by 2. 108 times 2 is 216 over, this is 4 and 1, so we've got nothing there. 1 times 125 times 5, 125 times 5 is 625. plus over here we've got 81 on 625, so we've already got a nice common denominator. We just need to add 216 plus 81, so 216 plus 1 is 217, and then plus 80 is going to be 297 on 625. Can't see any obvious common factors in that, so let's hope that's factorised. What have we got there? 2 marks, so definitely 1 for your answer here, and probably 1 for this, which is showing a number of things here. It's showing that the fact you're using this formula, you've recognised it's binomial, and that's why when you use this formula, this definition here becomes a little less important, because this second line here that I'm pointing at, but you can't see that. So this line here, we're indicating there that we know that this is binomial, and we're also identifying n and p in the formula, and so that can count as a substitution for writing the definition at the top, but I would always still define it. So I think probably 1 for knowing it's binomial and that's what you need to be able to work out, and then 1 for actually being able to work it out. Okay, part B. In a randomly selected group of 4 people, what is the probability that exactly 2 people have the SPGE1 gene, given that at least one of those people has the SPEG1 gene? Express your answer in this form. Okay, worry about the form we need our answer in later. So it's a conditional probability. We've already defined the variable up above, so we don't have to do it again. It's the probability that exactly 2 people have the gene, given that at least one person has the gene. Okay, so conditional probability, we need the intersection of those two things. If x has to equal 2 and be bigger than or equal to 1, the only way that happens is when x equals 2, so the intersection is probability x equals 2. And then we do that over the second thing. Now, given we're working by hand, much quicker to work out probability x bigger than or equal to 1 by doing 1 minus the probability that x is equal to 0. Okay, so then we're going to need to work some things out here. So probability that x equals 1 is going to be 4 choose 1 times 3/5 to the power of 1 and times 2/5 to the power of 3 over, we have 1 minus 4 choose 0, 3/5 to the power of 0 and 2/5 to the power of 4. Okay, quite a lot of simplifying to do here. What we want to think about a little bit here is what we're aiming for in terms of the form of the answer. So we want to leave our answer in terms of powers of numbers. So A, B, and C are positive integers, so positive whole numbers. So we're going to have a positive whole number to the power of 3 on the numerator over a different whole number to the power of 4 minus a different whole number again to the power of 4. So I'm going to leave, as I simplify this, I'm going to leave things as powers rather than try and actually work out what 2 cubed is and what, etc. Alright, so, oh sorry, I just changed that, didn't I? Sorry, I've made an error there, haven't I? Probability x equals 2 should be that numerator. So this is 4 choose 2. That's the power of 2, and that's the power of 2. Okay, 4 choose 2 I don't know off the top of my head, so I'm just going to quickly generate my Pascal's triangle down to the 4th row. So bearing in mind that this is the 0th row up here, so I've got 1 row there. Now I need the 2nd row, and the 3rd row, and the 4th row here. 6, 4, 9. Okay, so this is 4 choose 0, this is 4 choose 1, this is 4 choose 2, this is 4 choose 3, and this is 4 choose 4. So I'm going to need that one there, 6. I also obviously need the 4 choose 0, but I know that one. Okay, so on the numerator, I've got 6 times, now I'm going to leave this as 3 squared on 5 squared times 2 squared on 5 squared. And then we've got over 1 minus, now 4 choose 0 is 1, 3/5 to the power of 0 is 1. And so we've just got, so I'm just going to write that a bit more centrally under here, 2 to the power of 4 over 5 to the power of 4. Okay, so we're nowhere near what we need to be at the moment, but we want to recognise a couple of things here. So the first thing is on the numerator here, I'm just going to ignore the 6 for a minute because it looks like a bit of an outlier. But if you've got 3 squared times 2 squared, 3 squared times 2 squared, because they have the same power, that's the same as 3 times 2 all squared. And so that is 6 squared. And so that's how it's going to come together with that other 6. So on the numerator there, I'm going to have 6 squared. And then on the denominator, when you have 5 squared times 5 squared, you've actually got 5 to the power of 4. Okay, then let's get a common denominator on the bottom here as well. So I'm just going to go fairly slowly here. So this is 5 to the 4 on 5 to the 4 minus 2 to the 4 on 5 to the 4. Okay, so on the numerator, this is 6 on 1. So we've got 6 times 6 squared, so that's 6 cubed on 5 to the power of 4. And then on your denominator, you've now got 5 to the power of 4 minus 2 to the power of 4 all over 5 to the power of 4. And then if we multiply both the top and the bottom of this fraction by 5 to the power of 4, we're going to get rid of those fractions in fractions. And we're just going to have 6 cubed over 5 to the power of 4 minus 2 to the power of 4. Which is in the required form, which was a cubed over b to the 4 minus c to the 4. Now, be careful about what it asks you for. So does it ask you to find a, b, and c? No, it doesn't. It asks you to express your answer in that form. So there's no need to therefore go on and say a equals 6 and b equals 5 and c equals 2. That's not the question. We just needed to get it into this particular form. And we've done that. How many marks have we got here? 2 marks, so it's not many marks for quite a lot of work. Again, I think probably a mark about here, maybe a bit more generous to give it here, understanding and interpreting the conditional probability, and then a mark obviously for getting your final answer in the required form. Okay, so question 6, we've got a function here, has a restricted domain 0 to 2. F of x is 1 on root 2 times root x. Now to me, when I first saw this, that seems a really messy way to write this function. And I immediately thought, well, that's just root x on root 2. And that's just root x on 2. And then I tended to work with the function in that form, which perhaps made my derivatives look a bit different to what they might be if you had left it in this form. But I actually think ultimately it's still easier. So let's just think a little bit about what this graph looks like. We're going to have to find inverse functions and things, so always good to think about what you're dealing with here. So if we think about it in this way, it's a square root graph that's been dilated by 1 on root 2 from the x-axis. Or if we think about it in this way, again, it's a square root graph that's been dilated by 2 from the y-axis. So it's just a square root graph with a dilation. We've got that restricted domain though. So it only goes from 0 to 2. So obviously it definitely only goes from 0 to infinity, but it's restricted, it stops at 2. So if we think about when x equals 2, we go into this version, it's a bit quicker. When x equals 2, 2 on 2 is 1, square root of 1 is 1. So it obviously goes through the point 2, 1. So they're inclusive endpoints. Okay, so that's the function we're dealing with. And that's going to help us to think about our domain and range of our inverse and all of those sorts of things. So to find our inverse function, we need to first of all introduce y into the problem and then swap x and y. And we can do that all in the one step by letting f of y equal x. And so f of y is the square root of y on 2 if we use my simplified version. And then we can square both sides, so y on 2 equals x squared. And then we can multiply both sides by 2. And then we need to make sure that we answer the question, which is to find a rule for f to the negative 1. So it should be f to the negative 1 of x equals something. And we want the domain. Okay, so therefore, inverse of f is 2x squared. And the domain of the inverse is the range of the original function. And that's where it's helpful that we drew our original function. We can see that that range is 0 to 1. Okay, then you've also got a really big helping hand here because they've drawn the graph for you, and we already drew it ourselves up here, but it's drawn here. So there's absolutely no excuse for getting this domain wrong up here when you've got the graph drawn here and you can see what the domain and range of the original function was. So we've got the graph of the original function shown on the axis above. Sketch the graph of the inverse over its domain. Label the endpoints and points of intersection with giving their coordinates. Now, again, even if you couldn't answer part A here, everyone should be able to do part B, okay? We all need to understand that an inverse function is just a reflection in the line y equals x, okay? There's y equals x there. well, we want to reflect everything in y equals x. We can see that they're going to intersect here where that original graph crosses over y equals x. Okay, we don't even need to calculate the points of intersection. It does ask you to label the points of intersection, but we can see it, read it off the graph. Reflecting in y equals x switches all your x and y values. So the point 0, 0 is still going to be 0, 0 because the x and y value will change. The point 2, 1 is going to become the point 1, 2. And I recall in the examiner's report they mentioned the number of students worked out that the endpoint was 1, 2, but they didn't put it in the right place. So you've got to use the scale. So that's 1, 2 there. You can't have it anywhere other than that. Okay. So we're going to go through that point at 1, 2, which I've labelled with coordinates. We're going to hit this point of intersection here at half, half, and then we're going to also hit this point at the origin. So we want to be drawing that. We want to be getting that mirror image kind of shape. Okay. And so we've got our graph of y equals inverse f of x. Let's be clear about what we needed to label. Sketch the graph over its domain. Label the endpoints. Okay, I've got one endpoint labelled. I'm going to label the other one. I know it's already labelled, but it's not going to hurt to make sure that I'm being clear that I am going through that point. And the points of intersection with coordinates. Okay, so making sure they're coordinates. So the point of intersection here is half, half. Okay, so this is a 2-mark question. Now, I think this is probably an interesting marking scheme. Now, I've marked VCAA exams, but it has been 10 years. But at the time I marked them, there was a graph sketching question. And in the graph sketching question, there was quite a lot to be done to have the graph drawn correctly. And they awarded a half mark for each correct thing. But there's no such thing as a half mark being awarded in the exam. And so you tallied up the half marks, and then you rounded down to the nearest whole number. So I think this is a good example to think about that. If we think about this endpoint being worth half a mark, this endpoint at the origin being worth half a mark, this point of intersection being worth half a mark, and the shape being worth half a mark. And then you add all of those things up, and if it adds up to 1.5, you round down to 1. If it adds up to half, you round down to 0. If it adds up to 2, it's still 2. If it adds up to 1, it's still 1. Okay. And that was how they did it. So it can be quite punishing. You get only one thing wrong, you lose a whole mark. You can get 2 things wrong and still only lose a whole mark. But it's a way of making sure that everything is accounted for. I also recall in the examiner's report here, they talked quite a bit about shape. There did need to be that symmetry across y equals x. There was comments that people had the graph looking too vertical at the end point there. Okay, so making sure it doesn't get vertical, because it's still going to, in fact, mine might even get slightly a bit vertical there, because it is still going to keep going out this way. It's a parabola. So it's not going to be it's not approaching an asymptote or anything like that. Okay, but there's our graph, 2 marks. Find the total area of the 2 regions. Okay, so 2 regions. One region bounded by the functions f and inverse f. Okay, so the region bounded by the functions f and inverse f is fairly obvious. So my graph up here, that's going to be this. Okay, and then the second and the other region bounded by f, inverse of f, and the line x equals 1. Okay, so let me just maybe get a different pen color here. Bounded by f, inverse of f, and the line x equals 1. Okay, so x equals 1 is this vertical line here. And so we want to be bounded by the 2 graphs and that line, and so we're talking about that region in there. So we want to find the total area of the 2 regions. So we want to find the sum of both of those areas. Okay, so they're both relatively straightforward integrals. The first one, we could do it as the integral of f minus y equals x and then double it, but given that we're going to have to integrate inverse f to find the other region, we may as well just do the area between the 2 functions. So remember, area between 2 curves is always top minus bottom. So between 0 and 1/2, the top function is f of x and the bottom function is inverse f of x. So our total area is the integral from 0 to 1/2 is the first one. And as I said, the top function was f of x and the bottom function was the inverse. And then we're going to need to add that together with the second region, which isn't too complicated because it is still just an area between 2 curves. We're integrating from 1/2 to 1. The top function this time is the inverse and the bottom function is the original. We're doing that from a half to 1. Okay, so f of x, let's go back up to our original function. This is our f of x. We could use this version here, we could use this version here, which we'll need to at some point write with the power of a half, so I'm going to write it like that, x on 2 to the power of a half, so we can integrate it. So it's going to be integral from 0 to a half of x on 2 to the power of 1 half, minus the inverse, which was 2x squared, which is a bit nicer. And then we're integrating half to 1 of the inverse, which is 2x squared minus the original. Okay, so take your time, write out extra steps. You've got a whole page here, use it. You'll make mistakes by trying to skip steps. Okay, antiderivative of x on 2 to the power of a half. Okay, so what we need to remember is that and again, let's go to our formula sheet here rather than remembering. Our antiderivative of, and this is the formula that I find students use least and need most, this one here. It's this that we're dealing with here. Okay, so in our problem, we're integrating essentially half x to the power of a half. Okay, so in this case, we have a equals a half, and we have, a equals a half, and we also have n equals a half. And we're using this formula here. So our antiderivative is going to be 1 over a, which is a half, times n plus 1, which is a half plus 1, so 3 on 2. So it's going to be half times 3 on 2. And then we're going to have the original thing in the bracket, half x, and we're going to add 1 to its power. Okay, so over here, this is going to be 1 over a, which is half, and n plus 1, which is 3 on 2. And nothing changes in the bracket, and we add 1 to the power. Okay, so we've got that. Here we're going to add 1 to our power, x squared becomes x cubed, and divide by that new power, so we're going to have 2x cubed on 3, and we're doing that from 0 to a half. And in the second bracket we've got the same functions, they're just the other way around. So it's 1 on half times 3 on 2, that's x on 2 to the power of 3 on 2, and we're doing that from half to 1. Okay, let's just tidy those up a little bit before we do the substituting. So half times 3 on 2 is 3 over 4, and if we've got 1 divided by 3 over 4, that's 4 over 3. So we've got 4 on 3, x on 2 to the power of 3 on 2, minus 2x cubed on 3. And again, this will be 4 on 3. Okay, so now we want to do our substitutions. So substituting in 1 half, we're going to have 4 thirds. 1 half divided by 2 is a quarter. And then this is 2 thirds times a half cubed. And then if we're taking away, if we put 0 into both of those, we'll get 0. Do just think that through though. Sometimes it's a common habit. Students just assume that when they sub 0 into anything, they'll get 0. But if it's cos x, it's not 0. If it's e to the x, it's not 0. So do just think it through carefully. But in this instance, putting a 0 in here and here will mean we have 0 take away 0. Okay, in the second bracket we're going to put 1 in, so that's just going to be 2 thirds minus 4 thirds times a half to the power of 3 on 2. And then, sorry, I didn't mean to have a square bracket there, doesn't really matter, but, and then we're taking away and subbing in a half, which will be 2 thirds half cubed minus 4 thirds, again, half divided by 2 is a quarter, to the power of 3 on 2. Okay, again, take your time. Just write it all out, deal with each term separately, make sure that you're comfortable with each step. Okay, so power of 3 on 2. So remember, if we have a power of 3 on 2, that's 2 things at once. That's a half times 3, which means we can think about it as x to the half and then cubed, or the square root of x cubed. So if we have a quarter, the square root of a quarter is a half, and then we cube that, we're going to have an eighth. So this is going to be 4 thirds times an eighth, minus, this is 2 thirds times an eighth as well, because a half cubed is 1/8. Minus 0, so we'll ignore that. Plus, in here we've got 2/3 minus, now this is the same, oh no, this one's not very nice. So it's going to be square root and then cubed. So actually in this instance, I might think about it the other way, because we could also think about it as cubing and then square rooting. And I might actually do it that other way here. So this one's going to be 4/3. If we cube a half, we get an eighth, and then it's going to be the square root of an eighth. Okay, now here we've got 2/3 times 1/8 minus 4/3 times square root is half and cubing is an eighth. Again, take your time. Okay, 4/3 times 1/8, the 4 and the 8 will cancel down so that we've got 1/2 essentially, so it's going to become a sixth. And then minus the 2 and the 8 cancel down, so we have 1/4, so that's a 12th. Now, I think we've got a particular form we want this answer in, don't we? Okay, so we want it to have, it'll have a surd in it, and that's going to come because we've got this surd happening here, but we do want that surd to be on the numerator. So let's sort of perhaps focus a little bit on what's happening there. So we're going to have 2/3 plus 4/3 times, now square root of 1/8 is square root of 1, which is 1 over the square root of 8, and the square root of 8 simplifies to 2√2. Alright, let's just keep going here. We've got these sames, 2/3 times an 8th is a 12th, minus 4/3 times an 8th is a 6th. We did those in the earlier bracket. Okay, so 1/6 times 1/12 is 2/12 minus 1/12, so that's just 1/12. Okay, so then in here we've got 2/3 plus, now that's going to become 4/6√2, but there's a common factor of 2 there that we can cancel down, so that's going to become 2/3√2. Minus, now a 12th minus a 6th is 1/12 minus 2/12, so that's negative a 12th, so it's minus minus a 12th, so we're going to have plus 1/12. Okay, let's add together our 2/12. We've got 1/12 plus 1/12 is 2/12, which is a 6th. We can lose these brackets now, everything's addition, plus 2/3, plus, now we want that surd in the numerator, so I'm going to rationalise the denominator here, which means multiplying both the top and the bottom by √2. So that's going to give me 2√2 over 3 times 2 on the bottom, and then those 2's are going to cancel down. Alright, let's add these fractions together here. So we've got 2/3 is 4/6 plus 1/6, so we've got 5/6 plus, actually let's not cancel down those 2's there because we want that common denominator, plus 2√2 on 6, and so we put that together and we have 5 plus 2√2 on 6, which is in the form required, and the form required was minus. I made a mistake up here. See? So I made a mistake from here to here, so that should be a minus, minus, minus. Sorry. And so here we'll have a minus, and here we'll have a minus. Alright, so now let's check we're in the right form. So our form should be a minus b root b, so that's important too. It is 2√2, so the number there should be the same, over 6, and it confirms the denominator should indeed be 6. So it's definitely in the right form. Now, we've got 4 marks there. There was a lot of work in that. Let's think about what those are going to be. So obviously we're going to get one for getting to this final answer. I suspect the other 3 might all be quite early on. Given that we had to find a total area of 2 regions, I suspect that there would be 1 mark for integrals representing 1 mark for each of the regions, okay? And then probably a mark for the antiderivative. So, you know, whatever form, but essentially that, and it's essentially the same antiderivative, it's just a subtraction down the other way, round the other way. So the 2 separate integrals, 1 for correctly antidifferentiating them, and then 1 for simplifying it to the required form. And this is where it's also important to understand that even though there's a lot of work to get from that mark to that mark, if you can't do that, that's fine, but do at least set it up. Don't get bamboozled by the fact that you're being asked to give an answer in a particular form and you don't know how to do that. Forget that. Just start by setting it up. There might be a mark for just setting up the right integral. Even if you don't know how to integrate it, that would probably be worth something. If you can integrate it, great. That's probably then worth something else. If you can't then do the number work and the simplification to get at the required answer, I suspect you've probably still earned 3 of the 4 marks without being able to do that. Now, obviously it depends where the marks were in fact allocated. But I think this is probably a reasonable assumption. Okay, question 7. Consider the function f of x equals x squared plus 3x plus 5. So it's a quadratic. We've got part of it drawn here. And we want the point P10. Okay, given that I can see the equation, I know that point there is 0, 5. So, I mean, obviously we don't need the same scale on both axes. So I might actually, just for the sake of the diagram, put P somewhere here. We could work out where that turning point is as well, but just to give scale things accurately, but let's not worry too much about it. So let's say this is P. Show that the point P is not on the graph. Now it's really obvious from the diagram that the point P is not on the graph, but what we want to do is show that when x equals 1 in the function, the y value does not equal 0. Okay, so we want to do f of 1, which would be to show that. So let's be explicit here about how we do f of 1 and what that actually means. So that's 1 plus 3 plus 5. Let's try and get your handwriting a bit neater than that. 1 plus 3 plus 5. And so that is 9. And so therefore, since f of 1 does not equal 0, the point 10 is not on the graph. It's really important to note that this bit here is just as important as this bit here. It's a 1-mark question, but you're going to need both of these things. It's not enough for you to just do a calculation, to just do this, and then expect me as the person marking it to infer what that means in relation to the question. You're being asked to show that P is not on the graph, and so therefore, so in fact I haven't referenced P in my answer, the point P10 is not on the graph. So I've shown that f of 1 is equal to 9, and then I've made the observation that because f of 1 doesn't equal 0, the point P, which is 10, is not on the graph of y equals f of x. So those 2 things are going to be needed to earn that 1 mark. A calculation to support the statement, and a statement to interpret what the calculation's doing. Consider a point Q with coordinates a, f at a to be a point on the graph of f. Okay, so let's just stick a point somewhere. So let's say this is Q here, and it's going to have coordinates a, f at a being a squared plus 3a plus 5. Okay, so we want to find the slope of the line connecting points P and Q in terms of a. Okay, so we want to find the slope of this line, which is rise over run, difference change in y over change in x. Okay, so the gradient from P to Q is the difference in the y values, so that's a squared plus 3a plus 5 minus the y value of P is 0 over the difference in the x values. The x value at Q is a, and the x value at P is 1. So remembering when you use your formula for gradient, these must be from the same point and these must be from the same point. We could have written it as 0 minus a squared plus 3a plus 5, making sure that's in brackets, over 1 minus a. It would be exactly the same thing. Okay, let's just tidy this up a bit. So we've got a squared plus 3a plus 5 on the numerator over a minus 1 on the denominator. Okay, so that's the slope of the line connecting P and Q. Find the slope of the tangent to the graph of f at point Q in terms of a. Okay, so the tangent is this line here, okay, and that has the same gradient as the curve at the point A, at the point where x equals a. So therefore, the gradient of the tangent is the derivative at a, okay, and the derivative of x is going to be 2x plus 3, and so therefore the derivative at a is going to be 2a plus 3. Each of these two questions is just 1 mark, so just 1 mark for your answer. Okay, then part 3, let the tangent to the graph of f at x equals a pass through the point P. Find the values of a. So at x equals a, so that's at q, okay? So let the tangent to the graph of f at point q pass through P. Okay, so what we need to think about here is, obviously where I've drawn q here, the tangent is not going to go through P. But if we were to think about perhaps moving q, much further up over here, and drawing the tangent to the graph up here, it's not the best, not really on the right thing, it's going to go through P, okay? So what we want to think about is where this line here becomes the tangent, and hence the line from P to Q is the tangent, and therefore the gradient from P to Q is the gradient of the tangent. And hence that's why these are all part of the same question, part 1 and part 2 and part 3. Okay, so this means that we want the tangent, we want the line PQ to equal the tangent. We need line PQ to be the same as the tangent, which means that the gradient from P to Q is the same as the gradient of the tangent. And we've got expressions for both of those up here. So we've got a squared plus 3a plus 5 over a minus 1 is the same as, what was the other one? 2a plus 3. And we need to solve that for a. So we can have a squared plus 3a plus 5 equals 2a plus 3 times a minus 1. Let's expand out the right hand side. I didn't realise I had a little space. A squared plus 3a plus 5 equals 2a squared minus 2a plus 3a, so that's plus a and minus 3. And let's collect all those like terms. So taking away a squared leaves us with a squared, taking away 3a is minus 2a, and taking away 5 is minus 8. Okay, so we get 0 equals a minus 4 and a plus 2, factors of negative 8 that add up to negative 2. And so therefore a is 4 or a is negative 2. Now let's just think about any restrictions for a. Can a be negative 2? So what we're seeing here is if a equals 4, we're going to get a tangent up there. And if a equals negative 2, we're also going to get a tangent over there. Okay, which makes sense, fits the diagram. Does my answer make sense? Go back on what you're looking at here. There's nothing here to suggest that a can't be both of those things. And the question does ask me to find the values of a. And so therefore we've got two values of a equals 4 and a equals negative 2. And we've got 2 marks. So obviously 1 mark for the 2 answers, 2 values of a, and 1 mark for equating your 2 gradients or some other method. So that would be a method mark here, setting up an appropriate equation or using an appropriate method and then arriving to the correct answer. Give the equation of one of the lines passing through the point P that is tangent to the graph of f. Okay, so here you have a choice. There's actually 2 different correct answers and you don't need to do both of them. I'll calculate both here, but you only need one to earn the mark here. So when a is equal to 4, we want to give the equation of one of the lines passing through the point P that is tangent to the graph of f. When a equals 4, we know that it goes through the point P, and P has coordinates of 1, 0. So y minus 0 equals, sorry, the gradient won't be a 4. We need to work out the gradient. When a equals 4, the gradient of the tangent, let's go back here, gradient of the tangent, remember, is 2a plus 3. That means the gradient of the tangent is 2 times a plus 3, so 2 times 4 plus 3 is 11. Okay, and so the equation, y minus, we're going through the point P, which is 1, 0. Y minus 0 equals your gradient, x minus your x coordinate, which is 1. And so that's y equals 11x minus 11. So that would be one correct answer. Or we know when a equals, what was the other answer? Negative 2. Yep. when a equals negative 2, the gradient of the tangent is 2 times negative 2, which is negative 4 plus 3, so it's negative 1. Again, thinking about the diagram we drew up here before, I've rubbed it off, but it makes sense that this one had a gradient of negative 1, this one had a gradient of positive 11. Okay. Where am I here? Here we are. Gradient's negative 1, so y minus the y coordinate of point P equals the gradient times x minus the x coordinate of point P, and so that's y equals negative x plus 1. Okay, so you didn't need to do both of those, you only needed to do one. Okay, so it's either or. Find the value of k, that gives the shortest possible distance between the graph of the function of y equals f of x minus k and the point P. Now, you can spend a lot of energy here coming up with an equation for the distance and minimizing the distance, and there's some strategies about how I would do that efficiently, so I might actually show you how to do that. But actually the best way to do this is to really think about what this is asking you. So f of x minus k, we need to make a left or right translation, is what it's asking us. So how much should we translate f of x to the left or the right so that we're making the shortest possible distance between the graph and the point P? Now let's go up to our original graph here. So point P, just rub off some of these other things that we don't need anymore. Point P is on the x-axis, okay? So at the moment, if this is f of x, which it is, the shortest distance to f of x, so that is obviously when k is 0, because we haven't translated it left or right at all, is going to be sort of something like that. You know, there'll be some sort of distance there. But if we think about it, if I can translate this graph as much as I want left or right in order to get the graph as close as possible to P, given that P is fixed on the x-axis, if I can move it so that the turning point is right above P, that's going to be the shortest possible distance I could make. Okay? So actually, it's really just about finding the turning point. And we could do that by completing the square. Or have we already found? No, we could do it. We've already got our derivative, haven't we? Our derivative is 2x plus 3. So we could think about that the turning point, and so the turning point therefore is at negative 3 on 2. You could also complete the square, but we had the derivative and it's a nice easy solve. Okay. So therefore we know that the turning point is when x equals negative 3 on 2. So we know that the min turning point of f is at x equals 3 on 2. Min distance between P and f of x would be when the turning point is vertically above the point P. And so therefore, if we know P is at, we know the turning point is back here at negative 3 on 2, and P is at 1, we're going to need to translate this by this much, from negative 3 on 2 to 1. Okay, so this means that we need to translate f of x to the right by 3 on 2 plus 1, which is going to be 5 on 2 units. And so therefore, sorry for the delay happening, k will have to be 5 on 2. So thinking really logically about it, you can think about what would have to happen in order to minimize that distance between the graph and P. So it is possible to, normally in a question like this, we'd be tempted to sort of set up an equation for distance and then derivative equal to 0 to minimize the distance. But the equation here is really unwieldy because you've got f of x minus k, and if you think of the fact that, you know, f of x minus k in itself is x minus k all squared plus 3 times x minus k plus 5. You get a lot of k's and a lot of terms that need to be expanded and collected, and you end up with something so unwieldy that it's not manageable. So actually, really, this is one of those lessons in stop and think about what the question's asking you. What does it look like? What is happening? And what logically makes sense here? This is only a 2-mark question, and the algebra you would need to wade through is literally going to take you most of the exam. So thinking logically about the graph and how do I get the graph as close as possible to this point here at P, simply by doing a horizontal translation, and that would be to move the turning point so that it is directly above P, and that happens when K is 5 on 2. Okay, let's have a look at question 8, which I suspect will be the last question for the paper. So part of the graph of y equals f of x, where f is bigger than 0, is shown. The function is x times log e of x, and we've got the graph drawn for us. The graph of f has a minimum at the point a f at a, labelled q, as shown above. Find the coordinates of the point q. So we want to find the coordinates of the minimum point, and so we want to solve derivative equal to 0. Okay, so if we differentiate here, it's a product rule, x times log e of x. So we differentiate x, which is 1, and we leave log e of x as it is. Again, check your formula sheet for your product rule if you don't know it. And we add, and we leave x as it is, and we differentiate log e of x, which is 1 on x. So we're going to get f dash x is log e of x plus 1. And then we want to solve that equal to 0 for the turning point. And so that is log e of x equals -1. Changing it to an exponential equation would mean that x equals e to the power of -1. So we want the coordinates of point q. So we've got the x coordinate. And so then we obviously want f of e to the -1. And so that is e to the -1 times log e of e to the -1. Now log e of e to the -1, that -1 can come down the front. -1 times log e of e, and log e of e is 1. And so this is just -1. And so we have negative e to the -1. We could also write that as 1 on e, and we could also write this as -1 on e. So therefore q is e to the -1, negative e to the -1, or 1 on e, -1 on e. Makes sense. Positive x coordinate, negative y coordinate fits where it's sitting on my graph there. Okay, so we've got the coordinates of point q. It's a 2-mark question. Again, I think probably 1 mark for correct derivative equal to 0, and then 1 mark for coordinates. Using the fact that the derivative of x squared log e of x is 2x log e of x plus x, so we could have been asked to show that ourselves, but we're not, we've been given that. But using that fact, show that x log e of x has an antiderivative of this. Okay, so we want to use this derivative fact, and so I'm going to actually start with that derivative fact. If the derivative of this yellow thing is this green thing, then that means that the antiderivative of the green thing, 2x log e of x plus x dx, is the yellow thing. You always want to start with that, simply reversing the statement about the derivative. If the derivative of a is b, then the antiderivative of b is a. Done. Now let's focus on what we're trying to isolate. We want x log e of x, so let's focus on splitting up this integral on the left-hand side. So it is the same as 2 times x log e of x dx plus the integral of x dx. And we know that that's x squared log e of x. Alright, antiderivative of x. So we're going to subtract that. We're going to have x squared log e of x minus the antiderivative of x. And the antiderivative of x is x squared on 2. And then we need to divide everything by 2. So the antiderivative of x log e of 2x is x squared log e of x on 2 minus x squared on 4, which is what we were being asked to show. So to show that, so remember the mark is for process, okay, not for the answer. So reversing the derivative information and then showing that that can be manipulated to give the required answer. Part C, find the area of the region that is bounded by F, the line x equals A, and the horizontal axis for x between A and B, where B is the x-intercept of F. Okay, so F, the x-axis, x equals A. Okay, so this is the line x equals A. So F, x equals A, the horizontal axis from 0 to B, so we're looking at this bit of area in here. So we recognise that it's an area under a curve, so it's the negative integral of f of x from A to B. Okay, so the area is the negative integral from A to B of f of x. I prefer, rather than doing negative integrals, to reverse the limits from B to A of f of x. Now we already worked out A in part A. A is the x-coordinate of the turning point, which is e to the negative 1, or 1 on e. But we need B, which is the x-intercept. Okay, so f at B is 0, that's the x-intercept. So that means B times log e of B is 0, dividing both sides by B, because B clearly isn't 0. Log e of B is 0, so e to the 0 is B, which means B is 1. Okay, so that means we're integrating from 1 to 1 on e. I might write that as e to the negative 1. Just a bit neater in there. And f of x is x log e of x. Now in part B, we've just shown what the antiderivative of x log e of x is, so we want to use that. Antiderivative is x squared log e of x on 2 minus x squared on 4, and 1 to e to the negative 1. Okay, let's substitute. So it's going to be e to the negative 2 log e of e to the negative 1 over 2. Take away e to the negative 2 on 4 minus 1 times log e of 1 over 2 minus 1 on 4. Okay, so I don't like these big fractions. E to the negative 2 is 1 on e squared, so I'm going to have 1 on 2e squared out the front. And then log e of e to the negative 1, again that negative 1 comes down the front, and log e of e is 1. And so that whole thing is just negative 1. So we're going to have that minus, again this is 1 on 4e squared. Take away, log e of 1 is 0. So that's 0, it's just going to be negative a quarter there. Okay, so we get a common denominator here fairly easily, so this is just negative 2 on 4e squared minus 1 on 4e squared, and that's going to be plus a quarter. Okay, so that's negative 3 on 4e squared plus 1 quarter, or we might write that as 1 on 4 minus 3. Or you might get a common denominator, multiply the first fraction top and bottom by e squared, so you'd have e squared minus 3 on 4e squared. Okay, so definitely 1 for the answer. How many marks have we got here? Only 2 marks. Okay, so again, it's very light on. Hard to say. Possibly for setting up, the integral and then just getting to the answer, because there's a bit of work in the integral. You had to work out b equals 1 to get that there as well. The first mark might be for actually that antiderivative, recognising the connection to the antiderivative in part A. It's hard to know. But that first mark, I would say I think it's enough to sort of recognise what integral you're being asked to find, and including the fact that b equals 1 in it, and then getting to the final answer. But yeah, it's pretty light on for marks. It's definitely worth more than that. But again, that's what tends to happen towards the end of the paper. The questions tend to be a bit light on for marks because we're aware that these are the differentiating questions at the end. Some students aren't going to get to them at all. Some students will get to them but not be able to do much with them. We can't make them worth 4 or 5 marks. Okay, and then part D, let G, which has a domain from A to infinity, be f of x plus k. So that's simply a translation up or down. So we want to think about translating our graph of f of x, which we've already got drawn up here, up and down. Okay, so we already know, just going to delete that stuff that we don't need now. We already know that this point here is 1 on e, negative 1 on e, and we know that this point here is 1, 0. So, part 1 of this question, find the value of k, so how much would we have to translate f of x up or down by, for which y equals 2x is tangent to the graph of g. Okay, so let's go back up to our graph again. Okay, so y equals 2x is going to look something like that. So the question is, how far up do we have to shift this so that this shape is tangent? Okay, so what I'm going to think about instead is, essentially what I want to know is, where is the gradient of f equal to 2? Okay, so let's say, for example, that the gradient of f is equal to 2 at, now I'm not going to get this right, it's not going to be the right point, but let's say it's here. That means whatever the coordinates of that point are, we'll need to shift the graph up by that amount so that it's going to have a gradient of 2 hitting y equals 2x. So what we want to find is, on f of x, where is the gradient equal to 2? That's the first thing we want to find. Okay, so we want to know, where does the derivative equal to? We've already worked out our derivative. It was log e of x plus 1. We want that to equal 2. So log e of x is equal to 1. E to the 1 equals x. So x equals e. And therefore f of e is e log e of e. It's also e. Okay. So gradient equals 2 at the point EE. Okay. So I was probably roughly on point with my diagram I drew before. Okay, so E is 2.718, so it's almost 3. So let's say this is EE here. The gradient at this point is 2, which means the tangent at this point will be parallel to the line y equals 2x. Okay, and so what we're going to need to do is we're going to need to shift the graph up by this amount in order to make sure that, so we're going to need to go up by actually, we don't know how much we need to go up by yet. What we really need to work out is, we could do a couple of things, but what would be the best thing is, I think, to work out what is the y-intercept of this tangent, and then that's going to tell us how much we need to move the graph up by in order to get the tangent essentially to be y equals 2x. So if we work out the tangent when x is equal to e, so let's go back here. Okay, so if we do the equation of the tangent at x equals e, we already know the gradient there is 2. We know the point, so the equation is going to be y minus the y coordinate equals the gradient times x minus the x coordinate. So that's going to be y equals 2x minus 2e plus e, so minus e. Okay, so therefore the y-intercept of the tangent is negative e, and we need it to be 0, and so therefore we need to translate the graph up by e. Okay, need to translate up by e units to make tangent y equals 2x, and so therefore k is going to have to be e. So it's quite a bit of work and thinking for 1 mark, but again, like I said in the previous question, I tend to get a bit stingy with the marks later in the paper. The questions are generally worth more than that, but we don't want to overly penalise the students who don't get to this point or can't do this. Find all values of k for which the graphs of g and the inverse of g do not intersect. Okay, so let's just again think graphically a bit here. So we've got g, which does this, okay, and that's 1, and the inverse of g would do that, and that would be 1, and so clearly they intersect. Okay, so again, it's about shifting k up. Sorry, k is about translating the graph up. So if you were to translate the graph up, so let's say that was, 0, 2, which would make that 1, 2 in the original graph, then you would have 2, 0 and 2, 1, and your graphs wouldn't intersect at all. So what we want to think about is when they are going to intersect. And so what they're going, because it's the inverse and it's original, we know they're going to intersect on the line y equals 0. Okay, so what we need to think about is translating f up enough so that so y equals x is tangent to it, because then when that happens, the inverse will also be, let's try that again. The inverse will also be tangent to it, and therefore they'll meet once. Okay, and that will be the point where they're going to just touch, and then if we want them to not intersect, that's what the question's about, so we would then want k to be bigger than that value, so we'll need to translate by more than that. So we want to try and think about this situation, what's the value of k that makes this situation, and then k is going to have to be bigger than that. Okay, so we need y equals x to be tangent. Oops. To y equals f of x. So y equals f of x plus k. But so we're going to do exactly the same thing as we just did in part 1, where we wanted y equals 2x to be tangent. Okay, so this time we want our derivative, it's y equals x, so the gradient has to be 1. I want to know where is the gradient 1. Okay, so that's when log e of x equals 0, so e to the 0 equals x, and so x is 1. And therefore f of 1 is 1 times log e of 1, and that's 0. Okay, so we actually have a gradient of 1 at p. Oh, sorry, at not p, whatever that x-intercept was called. Okay, so we then want to think about, same logic, what's the y-intercept of that tangent, and therefore how much would we have to translate it up by so that tangent becomes y equals x. Okay, so we want equation of the tangent at x equals 1. We already know the gradient there is 1. Y minus the y coordinate, gradient is 1. So that's y equals x minus 1. Okay, and so therefore we're going to need to translate the graph up. Up by 1 unit, which means k equals 1 for y equals x to be tangent. And so that means if we translate it, sorry, I lost control of that there. And so therefore k must be bigger than 1 for no points of intersection. Okay, so k must be bigger than 1. 2 marks there. So hard to know how, because there's probably quite a few different ways you could think about there. It's hard to know what that first mark would be for. If you followed the same logic as the previous question, maybe recognizing that you're trying to find when the gradient's 1, that's probably a bit simple. Maybe finding the equation of this tangent and recognizing what that means. Yeah, I'm not really sure where exactly that first mark would be, and as I said, it probably depends on what your solution process was. I'm sure this isn't the only way to go about it, but it's this thinking about, okay, they're going to just touch once when they are both tangent, when y equals x is tangent to both of them, and then, okay, so that happens when we translate up by 1, okay, and so therefore if k is bigger than 1 and we translate up by more than that, the two graphs are not going to intersect at all. So I think that's the end of the exam. So that is the 2020 Exam 1, remembering that this was a altered study design with a lot less probability, although Exam 1's often doesn't have too much probability in it anyway, and there was probably a fair amount of probability, that you would normally see in an Exam 1 in this particular example of a paper.